like to finish up the semester by talking a little bit about what's left to do, which is a lot, what you might want to study in the future. And let me start off by sort of looking at where we are now and what I think you should all be able to do at this point. So what we've done is we've been with WebGL, we can create pretty nice 3D applications. We can integrate it with a lot of other packages that are available with HTML5 because the canvas is part of HTML5. So many of you, I notice I've seen that in your projects. You're familiar with that. For those of you who are not, you can bring in a lot more by bringing in CSS to get some much prettier styles involved, using jQuery to do a lot of your input. So there's an awful lot you can build on with what you have now. But the fundamentals of 3D, that's what we've been focusing on. You should be very good at this point at working with event-driven input. I know in the past that's been fairly new, but I think with what I've seen with your projects is that because a lot of you have worked with the web, that it's not quite as big a departure from what you've done before in your programming courses. What I think is really important of what we try to emphasize in this course is a lot of texture-based methods, because that's really where the action has been occurring in computer graphics. And that includes a lot of what we've been doing with off-screen rendering. If you look at some of the things that you could be doing, I mean, that's really where a lot of it is. Now, what we haven't done is talk with a lot about some other OpenGL capabilities. Now, I'll talk in a minute about, in particular, what that means with desktop OpenGL. I think you have a pretty good picture of what's available with WebGL. And WebGL, I expect, because of the enormous interest in it, that what's available within WebGL is going to continue to grow over the next few years. What we haven't really talked a lot about, which is important but generally doesn't fit into a first course on computer graphics, is really talk about modeling. What do we do at the high end in order to build models that we're going to work with, kind of things that we do in CAD. We've seen some of the basics. We can deal with meshes, but we really don't have good modeling tools to build complex models. We've sort of given you a few hints here. So one of the things you might want to look at for those of you who've done modeling or are interested in modeling is to look at Three.js, because that is really used a lot by modeling people. Also to look at scene graphs in general. The Three.js is just one of them, but I think scene graphs are really a higher level to work with, and OpenGL is then the layer underneath to do the graphics. We talked a little bit, this week about alternate renderers, and one of the things I hope many of you will do is take the course that talks about ray tracers, and if you look at the kind of research that's going on, a lot of the other kind of rendering strategies are very, very important. As we said in the last slide, integrating with other WebGL applications, I haven't spent a lot of time in. There's just a limited amount we can do in this course, but I think or should be able to find where to go for that. But I also look a little bit about where things are going, and first what's in desktop OpenGL that we didn't study here. First, that there's a number of new kinds of shaders available over the last 3 or so years. We've had in desktop GL, OpenGL, geometry, tessellation, and compute shaders. Geometry shaders let you do things like one of the limitations of what we've had is that every time a vertex is generated, you generate an execution of the vertex shader. But that means it's kind of one-to-one. You can't generate more than that one vertex. You have the possibility of throwing it away, but generally what happens is each vertex generates one vertex that then gets sent on through primitive assembly and on to the rasterizer and the fragment shader. Now, a lot of things you want to do, like when we talked about curves and surfaces, is you'd like to have one uh, one vertex or perhaps a couple of vertices, like when we talked about control points for polynomial modeling for curves and surfaces, generate a lot of intermediate vertices and not do that in the GPU, but do that automatically not do it in the CPU, but have those extra vertices generated within the GPU. Well, you can do that with a geometry shader. You can also do that with tessellation shaders. What tessellation shaders let you do is pass in a whole lot of vertices that might, for example, describe a polygon that's more complex than a triangle, even with some of the vertices describing holes in that triangle, and breaking that up into small triangles, which can then use the rest of the rendering pipeline. So there's a lot more complexity in the pipeline that's being built in. Now, what we'll talk about here and there in this lecture is the idea of using the GPU as a compute engine. Because the GPU has such incredible speed, we would like to be able to sort of send off floating point computation jobs to it. And one of the things we're seeing is more and more floating point capability in the GPU, both from going from 32-bit to 64-bit, and also being able to have floating point frame buffers and floating point textures. So that opens up all kinds of possibilities that are not necessarily coming from graphics applications. So what's occurred recently, and now that's coming into OpenGLES, is a compute shader, which isn't like the other shaders, which are part of the pipeline, but are essentially co-processors in a sense, where you can send off some computing job off to the compute shader and get the results back, and they're not done on a vertex by vertex basis. The idea is you have this compute shader sitting there and you can send some computation off to it. So that's something that's very, very interesting and very exciting, and we'll see it pretty soon in WebGL. Now, if you look at what's in desktop to OpenGL now and what's happened sort of independently of these new kinds of shaders, is there's a lot of emphasis on texture functionality, a lot of options that you can put in there, things from different formats that arise in applications like games that aren't the standard RGB format, to be able to take things in at different resolutions, even to do some compression with textures. So one of the things you see is not necessarily a whole lot of more capabilities than we've studied, but rather a lot more options that will allow you to do things much faster. What you do have in desktop OpenGL is 1 through 4 dimensional textures. We've only had 2-dimensional textures available, and in particular 3-dimensional textures are really powerful things for not only for simulating materials by specifying sort of a block that has the right properties, but also for doing things like, for example, medical applications, doing visualization of CT data sets and MRI data sets. So that's a very powerful facility, and I expect that that'll come up in WebGL soon. One of the things that's in there is vertex array buffers, which were somewhat required in desktop OpenGL. It's sort of another level. We've had vertex buffers, but not vertex buffer objects, but not vertex array buffers. And it just gives you a lot more ability for a complex application to sort of group things together. There's also a lot of related functionality that's coming in, allowing you to share things among different program objects. So conceptually, we're not doing anything too much more than what we've had before, but in terms of efficiency of minimizing your code and being able to run things faster, a lot of these options are very important. One very important thing that's available in desktop OpenGL is the idea of an occlusion query. We mentioned that when we talked about scene graphs, that if you want to render things much faster, it would be nice if you could do a pass where you can eliminate a lot of things that you know will not appear. Instead of doing clipping, which will always work on everything, what you can do is do one pass and say, hey, all of these things were clipped out, so why bother to send them through the pipeline again? That's called an occlusion query. You find out that certain objects in your database are always going to be occluded, and we could simply throw them away and not pass all that geometry down the pipeline. So that's a very nice facility to have. Now, if you turn to look at what we're going to see perhaps in WebGL soon, a lot of these features are going to move, although they're moving in a different at different rates. So, for example, geometry and tessellation shaders were available in desktop OpenGL before compute shaders, but what we're seeing is that compute shaders are coming faster than geometry or tessellation shaders. Part of the reason is based on usage. People are finding compute shaders more important than perhaps geometry and tessellation shaders, for at least for a wider number of users. They were just released in the last month in OpenGL ES 3.1. 3.0 has been around for about a year, and so if we continue to see the path of seeing WebGL be an implementation of ES, then we can expect to see the things that are in 3.0 and 3.1 fairly soon. Another possibility is that there'll be some decoupling of WebGL from ES. One of the difficulties is that ES is supposed to run on very simple systems, very low power systems, embedded systems, and WebGL, if you're running it on your desktop, you say, well, I got this a lot of power here available, a lot of computing capability available here. I don't have to worry about low power. So sometimes the coupling of WebGL with ES is somewhat of a problem. I have no idea whether the standards committee is going to break those apart or not, but sometimes I say, gee, I really wish we'd get this facility in WebGL, and I don't really care about ES. Now, in terms of computation and using the GPU for computation, OpenCL was, CL being compute language, was a way of programming the GPU to do massive parallel computations, and OpenCL followed a couple of other things that were done with NVIDIA, but it's become very popular. And WebCL was released just last month, which now says that you can do these kind of calculations or use the GPU for other kinds of calculations. Now, perhaps the big difference here is between that and what I just said about compute shaders is that OpenCL and WebCL really allow you to exploit a very complex memory structure that's on the GPU. It's multi-level, there's caches, there's groupings of processors, because now we're starting to see hundreds and even thousands of individual processing units on the GPU, so there's very complex architecture. Now, to be able to fully exploit that, WebCL will do that, but it means that you have to really understand the architecture of your particular GPU, so your code, at least to be efficient, was probably not particularly portable to other graphics cards and other GPUs. Now my understanding of compute shaders is compute shaders will be a lot simpler to access and will not require you to understand that complex memory architecture. So we'll see how that stuff evolves. Now on the JavaScript end, there's a whole bunch of variants of JavaScript that allow you to write much cleaner, much shorter code. A number of my colleagues use CoffeeScript. They like that. But one of the things that we've been seeing lately is that ECMA script, which is the official name of JavaScript, has a draft of version 6. You're using version 5 in this class. And if you look at some of the things that are proposed to be in there, it becomes a much more, a language that's much closer to the kind of languages that you study, Java, C++. So some of the people who I know who have looked at that are very excited by what's coming down with that, and that'll pretty much, as soon as that becomes official, and I think you can even find some sample implementations of the draft in Firefox, and probably some people have done it for Chrome. So that's something to keep an eye on. Now, if you sort of back off and you look more generally at what's going on, there's a lot of things that happen, and I'll put this sort of under the category that the players have changed. If you look at the evolution of graphics hardware and software, it was originally completely dominated by the scientific community and the CAD community, because they had the workstations and they were the ones that were buying it. And OpenGL came through the workstation community as somewhat opposed to the PC community. That PCs and workstations evolved on somewhat separate paths, and now they've merged into where you get a box. It's just a PC, a workstation, no different. But when these standards started coming about in the 70s, the 80s, the 90s, through primarily Silicon Graphics was the place that a lot of these started. Not only the pipeline architecture, but also OpenGL came out of SGI. So the people who were making the decisions about what went into the standard were very much coming from this scientific and CAD community, computer science community. Now, when PCs became more powerful and we started getting graphics cards with GPUs on them, then everything really changed. And a lot of what happened was moved to Microsoft, and Microsoft in particular with people who were using that architecture for games. So you started getting a lot done within DirectX. DirectX was evolving very quickly, and unlike OpenGL, didn't really pay a whole lot of attention to backward compatibility, because there were people, in particular in the game community, who always wanted the latest hardware. And DirectX, which was much more complicated to learn, even though if you sort of look at it from a little bit of a distance, is using the same pipeline, but gives you a lot more control over memory and a lot of capabilities that were the latest things that were coming out in the graphics community. And for a while, that was really taking over because PCs and Microsoft were really dominating the field, and a lot of people thought OpenGL was going to disappear. Now that's all changed, but for a while that was really a worry that we all had. But what really still is true is that a tremendous amount of what goes into what you see available in graphics hardware and software is based on the demands of the game users and not on the demands of the scientific and the CAD community. There are other things going on in terms of architectures. For example, going back a ways, I think to the late 80s, the video toaster came about, which ran in I think in Amigas, and it showed that you could just generate real-time video in an entirely different way with hardware that you could afford and put in, and that was probably the first good example of things going in a very, very different path. But then as GPUs became more important, then the players really changed. So if you look at, for example, at the Standards Committee, when you used to see companies like Intel and SGI and some other graphics companies, many of which don't exist anymore, were dominating the standards committees and deciding what went into OpenGL. Now those committees are really controlled by companies like NVIDIA and AMD and Intel, which make the GPUs. So one good part of this is that OpenGL made this incredible comeback and is now pretty much the most widely used standard, because it'll run on everything. You don't have to have an Intel PC architecture to do it. You got from NVIDIA, you got things like GLSL. Kind of really came from CG, which was just short computer graphics, which was the language that NVIDIA created to control their GPUs. But still, it was somewhat dominated very much dominated by the game community. Now we're seeing a real change in that the web has become incredibly important, and smartphones are becoming dominant. So if you look at, for example, what's going on in games now, the large-scale games that run on, or the companies that develop them, are not doing as well as they were a few years ago because everybody wants games that are now going to run on handheld devices and also run on the web. So now you're starting to find, if you look at the standards committees and who, where they're going and who the players are, you find that Google and Mozilla and Nokia and others companies all are dominating what's going on in software. Another aspect of this is that ARM, which is the company that makes or designs, they don't produce the chips, they design virtually all the chips that go into smartphones worldwide. There was something recently, I saw a number, their design chips are 1 billion a month going on, and your cell phone probably has 1, 2, or 3 of their chips. Now, the important thing there is these are very low. The thing that ARM knows how to do is develop low power chips to do things. So this is now, as smartphones become and other handheld devices become so much more important, that ARM has become a major player in what's going on. So there's sort of this ARM Intel competition going on. Now I'll come back to that at the very end, but what kind of things haven't we studied in this class? So let me just give you kind of a list of things, and then tell you a little bit about where you might go to find out more information. One of the things we haven't talked about that's also a big part of desktop GL is level of detail, is that you can have models that have different level of details on them. Now that's important in places, for example, if you're going to view something that if you're viewing it from far away so that the rendered object is very small, you don't need all of that detail. You don't want to process all that geometry. So you want to have models that have different levels of detail built in. In some sense, it's like conceptually what we had with MIP mapping and texture maps, but this is actually in terms of the meshing and the models that you're building up. So there's a lot of support for that in desktop OpenGL. Image-based rendering is a very big area now. In some ways, it's kind of going backwards because what you do in image-based rendering is you take a number of images and you try and extract the 3D model from that. So that become, in terms of what you may have seen in movies, that came about when you started seeing all these commercials and movies where an object, you saw a person that was frozen and the camera seemed to be moving around and the person was frozen in motion. That's image-based rendering. It's based on taking a lot of images and then somehow extracting, well, by interpolation, extracting the 3D object and then moving the camera to a new position. So there's just all kinds of applications of that. The Matrix was probably the first place that many of you saw that. Light field rendering, turns out, is fairly has a lot in common with that, where the idea is that if you could measure at every point in space, suppose you had an enclosed environment and you could measure at every point the light field, or what was incoming and outgoing at every point, that has all the information about all of the objects that are in the scene and the reflections and light sources. So there's a lot of interest in doing that, to do things like to re-render a scene with different lighting. If you could take a scene, try and figure out the light field, you could essentially undo it and then put different lighting in. The movie people really like that. They could shoot a scene, make all the objects in it, which were originally captured with whatever light was there, now remove all of the reflectivity and put in a new scene or a new environment and re-render the characters without having to reshoot the scene. So there's a lot of interest in that. Ray tracing we've talked about. CS413, this course that we've been doing is kind of a variant of 412. 413 is concerned with ray tracing and building your own ray tracer. Haven't had time to talk about visualization and volume rendering. A lot of this are the kind of medical applications where you capture a three-dimensional data set and you want to, which is a tremendous amount of data, and you want display that. So images I'm sure you've seen from head scans and other kinds of not just restricted to medical imaging. A lot of that has been done in New Mexico at the labs, and it's a very interesting field. Includes things like, actually the other place that comes up is in flows. If you want to see, for example, three-dimensional visualization of the flows in the ocean, or a lot of space applications, they fall within volume rendering. Now, point clouds are getting to be more and more interesting, primarily because you have a lot of technologies now that are very reasonably priced, in particular laser scans, where you can scan an environment and they'll generate in a fairly short amount of time literally millions and millions of points which have an XYZ associated with them. But they're unstructured. You just have a big set of points. So the thing is, how do you render those points? I mean, one way is you try and build some sort of a mesh out of those points, but with the amount of data that laser scans can generate, often that's a complex problem. Often you want to just render the points in some way where each point is not just rendered as a single pixel, but actually has properties like a direction, a normal, so that you can do things like shade the points. There's a lot of interest right now in point cloud rendering. I have a tiny bit of that in the book, and it's something I think, given the tools that you have from this class, you should be able to do some experimentation. One of the things that I've been trying to do, and a lot of people here are interested in, is particle systems, where you have these massive models, using massive in the sense of the number of entities, millions of particles moving around, and they turn out in fields like solving partial differential equations, physical simulations. It actually turns out to be, with modern graphic systems, to be more efficient and a lot more interesting to model things with particles rather than to look for some numerical method to solve some massive set of partial differential equations. There are also, for agent-based modeling, where particles have, each particle can have a different behavior, and there's a lot of AI involved in that. There are some very, very interesting things going on, and GPUs can handle millions and millions of particles per second. So that's a really interesting area to pursue. Information visualization is now getting to be more and more important. In some ways, it comes out of volume visualization, a lot of the techniques. But people are now, with big data, they're saying, how do we look at all this data? So there's the graphics community has gotten very, very interested in what's now being called information visualization. And if you, for example, look at some recent issues or some recent conference proceedings from SIGGRAPH, you'll see a lot of information visualization papers and a lot of conferences. Now, one of the things that I think got a lot of you interested in this is games, and what about games? Well, we've said that games or gamers are driving the hardware and software, but what does that mean in terms of what you might study in a course? Well, we tried to teach a few years ago. We started teaching Tom Caudell and I started teaching some game courses, interdisciplinary game courses here. One of the things that came out of that, they were a lot of fun, but one of the things that came out of that is, to really do a good job, you need more than one course, and you need a lot more material. And so some of the things you need, from the graphics end, you're not in bad shape. You probably would want to study some more real-time graphics. There's a lot more techniques that just to speed things up, because games need that speed. But there's a whole bunch of it which isn't particularly graphics in the sense we've been talking about it. So how do you develop your story? How do you do nonlinear storytelling, where depending on what the first person does, controls how the story is going to unfold? How do you develop those kind of stories? How do you develop your characters? And that's a whole separate area that's not hardware, software based, but is a very interesting area. And we did a part of the course on that, but you need to study that in more depth if you really want to develop your own games. Then there's the whole AI side of how do things behave, and that there's a lot of artificial intelligence involved. And I'd sort of like to see a course that actually was doing AI for games. And then the whole user interface business. I mean, we have not, HCI is a very important topic. It's a very interesting topic because it involves a lot of psychophysics of how humans perceive things and how do you best do things, which is, again, graphics touches on that, but it's a very important field on its own. And if you're really interested in games, you should be interested, or you should explore that area further. But more generally, if a lot of you are interested in working in the game industry, there's sort of two ways things have gone. In one sense, if you're looking at the really games that run on things like an Xbox, or these really big games, these game engines are really massive pieces of software. They're generally written in C++ still. There are millions of lines of code. So all the things that you talk about in your software engineering courses are really important in doing that. And these are things that are not developed by a single person. They're really huge pieces of software. Now, on the other end, the way things are going now is everybody wants to develop games for smartphones, and so those are sort of smaller applications, but are very efficient and use the GPU. So that's a really interesting area to explore. I think a couple of years ago we had a course in developing games for handheld devices that was taught as a special topics. Now, finally, I want to say a couple of things about supercomputing, which I find as a graphics person very interesting, because what's happened with the latest supercomputers that you see is that they finally realized in the supercomputing community that GPUs are an awful lot faster than the standard kind of Intel CPU architecture. And for example, one of the supercomputers up at, I think it's up at Atlanta, they replaced all the CPUs by GPUs. The CPUs just become controlled to get data out to the GPUs. And if you look at the fastest machines in the world, the top machines are really all have either CPUs or some other coprocessor available to actually do the floating point calculations. Generally, the speed of supercomputers is measured in how many floating point operations a second you can do, and they're talking about teraflops and petaflops for these machines. So it's very interesting that these things, the fastest one in the U.S., which I think is the second fastest in the world, uses NVIDIA GPUs in it. It's a GPU machine. Now you can do a little of that yourselves with things like look at OpenCL and look at compute shaders, because that's how you'll control them. How you actually write software for these machines is very complicated, and to a large degree it's not clear how we're going to be writing software in the future for these machines. But one of the things to keep in mind here is that the biggest problem now with developing better and better computers is the power issue. That we, a few years ago they discovered, well, we can't put more we can't get more and more bigger CPUs on it, but we can put a lot of processors on the chip. That'll keep the power requirement reasonable. So the power is sort of the dominant issue in development of not only supercomputers, but also what's going to go on the other end into your cell phone, which will be equivalent to a supercomputer of today in a few years. So, for example, the exascale machine that's being talked about now in DOE, they're talking about this machine requiring 20 megawatts of power to run it. That's an enormous amount. And so what kind of processors are you going to put in this thing? So that brings you back to the issue of Intel architectures versus CPUs that are coming out of companies like ARM that really understand how to do low power design. So there's a lot of very exciting things that I think are going to be going on in the next couple of years, and in many ways the kind of things that we do here in computer graphics, whether you're going to be working on a supercomputer or you're going to be working on a smartphone, aren't all that different. So I hope a lot of you are going to continue to pursue this area.